Hi, and in this video I'm going to go through Mechanics Unit 1 of Edexcel Physics, Materials Unit 1 of Edexcel Physics, ISP Task 4. So if you look at that, it's talking about the definitions of some key terms really. It's brittle, ductile, hard, malleable, stiff and tough. So that's the plan for this ISP task. So let's go down to explaining everything 4. So we're going to explain the meanings of tensile and compressive stress, tensile and compressive strain, strength, breaking stress, stiffness, and Young's modulus. So let's talk about these one by one. So remember, tensile is where things are being stretched apart, so that's by tension. So stretched apart by tension. And compression is where you're squeezing something together. So if you're making the length shorter, that's compression. If the length is being made longer, that's tensile. So talk about it in terms of length. So if you're having to define compression or tensile, talk compressive or tensile, talk about what's happening to the length. Stress, remember, is force over area. Strain is an extension over original length. So the strength of an object is essentially linked to how much force or how much stress it can take before, how much strain it can take before breaking, and the breaking stress is how much stress it can take before breaking. The stiffness is to do with how easily it extends when force applies to it. So the less stiff it is, the less it extends. The less stiff it is, the more it extends when force is applied to it. And the Young's modulus is the stiffness of a material, essentially. So stiffness is to do with a sample, more like, well, Young's modulus is to do with a material. So I've got some words over here in terms of brittle, ductile, hard, malleable, stiff and tough. Give examples of these materials, with these properties. Okay. So remember, there's a wonderful PowerPoint starting the VLE, so it's lesson 9, okay, which goes through all of this. So I'm just going to shrink the webcam for a second. Okay, and you can see all the words here and what they actually mean. So if you need to pause the video at this point, let me make this full screen. Okay, if you want to pause the video at this point so you can see these words a bit clearer, feel free to. Okay, but all the definitions you need are here. Okay, so I'm going to flick forward to some example materials with their graphs as well. That's right. There we go. Here we go, some example materials and their graphs. So if you need to pause the video to copy down some of these graphs, okay, you can do that too. But remember, all of these are available in the Edexcel book. Right, okay, so if you pause the video and got those down, that's great. Let's get stuck into the questions now. Let's go with this. Let's make the webcam reasonably big again, a bit bigger. Okay, and let's get stuck into these questions. So, where are we? Task 4. Okay, so the first one's like a comprehension, not comprehension exercise, a close exercise, where you have to fill the gaps in terms of using the words above. So, complete the gaps in the following paragraphs by selecting the appropriate words from the list. Increasingly, drinks containers are made out of polymers rather than glass. A container made from polymers such as polythene has several advantages over a glass container. Polythene has a low something, and so that something of the container is kept low. Let's give a low density, so the mass is kept low. Polythene is also something so that it can absorb a large amount of something before breaking. Whereas it can be tough, so it can absorb a large amount of energy before breaking. Glass is only strong under something forces, but polythene is also strong under something forces. Okay, so we've got to talk about the idea of compressive or tensile. So glass is only strong under tensile forces, but polythene is also strong under compressive forces. Okay, let's double check to see whether we've got all of these right. Yep, compressive and tensile for the last two, tough and energy for the middle two, and density and mass for the ones in the middle. Right, okay. Next one, okay, so body armour can be worn by police officers in 2 categories, hard and soft. Hard body armour gives protection but is heavier to wear and does not give the flexibility of movement. Circle the word that best describes the type of behaviour hard body armour is likely to demonstrate, okay, and state what is meant by the word you've circled, okay. So if it's ductile, it's going to be bent into wire, so it can't be that. If it's elastic, it's going to return to its original shape, and it can't be that. If it's plastic, okay, then it's going to deform upon impact. If it's tough, it's going to absorb a large amount of energy. So if it's hard, it's going to deform upon impact, but it's going to need a lot of energy to actually do this. Plastic is possibly the word that they're after. Okay, hard body armor is made from is inevitable, but does not give any flexibility or of movement. Oh, right, okay, so it's going to be difficult in terms of the word they're after. Let's double check. I'm pretty sure it'll be plastic is the word they're after, and the reason why is because it doesn't return to its original shape. Is there an explanation of what's going on there? Yeah, plastic, yeah, so that's the word they're after for that one. Plastic would be the word. Right, so hard body armor is made of rigid ceramic plates. Okay, ceramic plates are often described as being brittle. Why would this not be a desirable property for body armor? Because it breaks, so it shatters under impact, under large impact forces. It shatters. Many ceramics are not brittle, including aluminium, the ceramic material used in body armor. Okay, aluminium is a very strong material. What is meant by strong material? So again, idea of strength before is to do with, if I bring up the slide, you can see a really good definition of strength. So if it's strong, it's materials that need a large force to break them. Okay, so or require lots of energy to break them. They deform plastically, withstand large dynamic loads. Okay, so the idea is that this can deform plastically, withstand large dynamic loads. Okay, so in this situation over here, they're talking about Kevlar, and they're talking about a new fibre called BioSteel, which is being developed, that is several times stronger than Kevlar. The manufacturers claim that BioSteel can be 20 times stronger than ordinary steel wire of the same thickness. So here we've got ordinary steel wire. Calculate the maximum breaking stress that steel can withstand. Okay, so if it's 20 times as strong, the force it can withstand is going to be 20 times as much. Okay, that's the idea. So let's see how they're asking us to use this information to calculate what they want us to calculate. So the idea is we've got our stress is equal to the strain times by Young's modulus. Okay, and then you plug your numbers in, the numbers that they've given you over there, they've given you in the question, and you end up with 2 times 10 to the 8 pascals. Okay, so it's 2 times 10 to the 11 times 0.001. Did they ask for the steel or BioSteel? I can't remember now, I'm going to have to look back at the question. That steel can withstand, so not BioSteel. So they're not asking for 20 times as much right now. So all I want you to do is to times it by 0.1%. So so essentially what they're saying, let me write this out very clearly for you, is Young's modulus is equal to stress over strain. So therefore stress is going to be equal to Young's modulus times strain. Okay, that is 2 times 10 to the 11, and that is 0.11%. So 0.1%. So remember, 0.1% is the same as the fraction 0.001, because to get rid of the percent you just divide by 100. So that's how you end up with 2 times 10 to the 8 pascals, or Newton per meter squared. Hence, show the force needed to break a steel wire of diameter 1 millimeter is 160 newtons. Okay, so we know the Young's modulus, we know the diameter, and therefore the cross section. Sorry, we know the stress, because this we've just figured out, 2 times 10 to the 8 pascals. That is equal, stress is equal to force over area. We want the force, we have the area from A is equal to pi r squared. Yeah. So we want the force, we have the area from A is equal to pi r squared. R is going to be half our diameter, so that's half of 1 millimeter, so that's pi 0.5, and remember it's times 10 to the minus 3 because of the fact it's in millimeters squared, so that's our area. So we do force is equal to 2 times 10 to the 8 pascals, sorry, force is equal to 2 times 10 to the 8 pascals multiplied by pi 0.5 times 10 to the minus 3 squared. So remember, we keep it in times 10 to the minus 3 because it's easier than sort of dividing by 1,000 and trying to figure out what it is in millimeters. Let's get our calculator across. So 2 exp 8. Okay, so remember exp is our times 10 to the way I write times 10 to the on these older calculators. Times by pi times by bracket 0.5, which is our radius, half our diameter, exp minus 3 because of the fact it's millimeters squared. There it is. Okay, so we end up with about 157 newtons. That's about 160 newtons, which equals 157 newtons, which is approximately equal to 160 newtons. Awesome, spot on the money there. So next. So remember to pause that calculation if you want to guide your way through it again. If the manufacturers of biosteel are correct, what is the maximum force needed to break biosteel fibre of the same dimensions as steel wire? Okay, so the idea is that it can withstand 20 times, it's 20 times stronger, so therefore it should be able to stand 20 times the force. So it is just literally 20 times the value that we've just been given. So 20 times by the value we've just been given. So therefore it's going to be somewhere in the region of 3,200. Okay, 3,200. State one assumption you made about your previous calculation. They've all got the same dimensions. So I would say about the fact that it's uniform. I would say uniform being the same one. I'm guessing they've come up with something else I've just missed. But uniform is usually the uniform wires are usually the one they go for in these situations. Yeah, let's have a look. So 20 times that. So yeah, so that's the same value as what I've got there. Now multiplied by 20, so 3,140. Okay, or 32,560 is used. There you go. Everything else with you've done exactly correct. Elastic limit is not. Oh, right. Okay, so this is obviously very straightforward. I don't know why I haven't. Oh, area remains constant. So that's exactly what I was talking about. In the sense of this uniform wire across. So that's the same sort of idea. Young's modulus still holds our breaking point. Okay, so Hooke's law is obeyed. Remember, Young's modulus is only really. Well, it's only uniform. The idea of it's only uniform can be extrapolated when Hooke's law has been obeyed. The elastic limit has not been reached, which is key in the fact that it's elastic behaviour taking place there. So that's the end of question 12. Alright, question 13. So we've got some cyclists. And we've got some airflow around them. So this is going right back to the start of this unit. So what will be the airflow around the body of the cyclist? Well, it's going to be laminar, okay, around these guys. What will be the preferred airflow? You want it to be laminar so they can go as fast as possible. Draw the possible airflow above and behind the body of a cyclist. Okay, so in racing position, it's going to be laminar. When it's sitting upright, it's going to be laminar to begin with, and then becomes turbulent behind him. What is the advantage of speed cyclists travelling very close together as shown in the diagram? They can streamline off each other and stay in each other's laminar flow, and therefore these people need to put in less work. Essentially, the people at the back put in less work because of this. Plastic or elastic, better describe the material of the bodysuit to be worn by the speed cyclist. Explain your choice. Okay, and then we've got the idea of wood tough or brittle, better describe the material worn by the helmet. So you definitely don't want brittle, you want tough. Okay, is the idea for that, and again it's to do with the fact that brittle means it shatters under large impact, while tough would mean it absorbs a large amount of energy. So let's check the bits that's been said for that one. Okay, so streamlined. So again we're talking about drawing at least one continuous curve over them. Remember, you should draw 3 lines, turbulent behind the cyclist, just like we were saying. Less drag on the cyclist, or airflow above bodies, more streamlined, or less work needs to be done. Less work needs to be done, like we were saying, so they don't need to pedal as much. Okay, so the bodysuit, I forgot to say this one, is plastic, it's elastic, because remember, if it's plastic, it's not going to stretch around their body, it's going to sit in a rigid position, and therefore it would lead to turbulent flow. If it's elastic, it's going to stick to the body, and therefore there's going to be less turbulent flow taking place. So we want elastic, so it wraps around them. And just like saying tough, because it deforms plastically before breaking, so in other words, it absorbs a large amount of energy, rather than causing any injury or shattering, which could hurt someone essentially. Okay, so that's question 13 done. Okay, and that is the end of ISP Task 4, with only Task 5 remaining for the Materials ISP. Thank you very much for listening, guys.